Question 5.3 is another past exam question, and to be honest, it's a bit of a pig. It's too hard, but it's still useful to go through, because if you can master this, then you can master, it's easier to master easier questions. So it's going to take me a while, but let me start with redrawing the figure. So you've got two guides. That's one of the guides, and the other guide is in this direction. And then there is a link connecting. So that's A and that's B. And what makes this problem a bit nasty is just the needless sort of trigonometry involved. It's not my fault, I mean, I said it. There we go. It's done now. 20 degrees, and this angle is 25. That's the guide. And this is, this angle here is 45 degrees. So that's the direction of the motion and of at A, and that's the direction of motion at B. So the velocities and accelerations of A will be along this direction, and the velocities and accelerations of B will be along this direction. Now the question starts by telling us that this velocity here, the velocity of A, the magnitude of it, is equal to 30 centimeters per second. And it gives you a hint. It says, well, it wants you to calculate the angular velocity of the link, so it wants you to calculate omega, also the velocity and magnitude of B, and the magnitude of the velocity of B relative to A, so that's the velocity of B relative to A, and we know that there's only one component of the velocity of B relative to A, and that will be in a perpendicular distance to the line between A and B, so it'll be in this direction. And it also wants to know what the centripetal component of the acceleration of B relative to A is. So the acceleration of B relative to A in the radial direction. So, and that will be in this direction. So that's what it wants us to calculate, and it tells us to first find the instantaneous centre. So this rigid body, which is the link AB, we know the directions of two vectors. If we draw lines that are perpendicular to those vectors on the rigid body, so that's one, and then, okay, I'm going to pretend that, just so I can fit it on our diagram, that that's perpendicular to B, perpendicular to the guide. Oh yeah, sorry, I've drawn that wrong. This is the velocity, the direction of the velocity of B, so I want a line that's perpendicular to that. So it's easy to get confused in this question with the trigonometry, and that's why it's not a very good question. And so that angle there is 20, that angle is 90, so it means that this angle in here is going to be 65. That's 65 degrees. And this angle is 45 because that's again perpendicular. That's the instantaneous centre. And 180 minus 45 minus 65 is 70. 70 degrees. So to find out before we can do any of this, these parts, we need to find out what these lengths are. So we know roughly where the instantaneous centre is, but we need to know exactly. This length is 0.2. It says it's a 20 centimetre link in the question. So that's 0.2 metres. To we've got the three angles of this triangle. It's not a right angled triangle, so we need to use the sine rule to work out what these lengths are. And I mean, it tells us in the question, hint, you'll need to use the sine rule, but still sort of a bit pointless. We're not really not supposed to be testing trigonometry here. So we know that, well, I'll write it up here, we've got a bit of space. Sine 70 over 0.2 is going to equal sine 65 over this length here, and we'll call it RA. So we can rearrange to find out what RA is going to be. So that will be 0.2 times sine 65, but I need to convert to radians, and then divided by 70 over 180. That gives us a length here of RA equals 0.193 meters. And we do exactly the same thing, but instead of 65, we use 45 to get the length RB. So we do that again. So instead of 65, we do it with 45. So that length is 0.151 meters. Okay, so far so good. Now we can use the fact that we know where the instantaneous centre is. We know that this velocity here, which is the velocity of A, is the tangential component of a fixed axis rotation around the instantaneous centre. So that means then the velocity, the tangential velocity of this fixed axis rotation is equal to the angular velocity, which is what we're trying to find out, times by this length RA, and we know this is 0.3. So omega is going to equal 0.3 over this length, 0.193. So what did I say it was? 0.3 over 0.193. That gives us an angular velocity of 1.55 radians per second. Now sorry, I've just gone off the end there. Let me just write the units underneath. Radians per second. Now, the velocity magnitude at B, we know what the angular velocity is. Now we use this length, so it's using the same equation, the tangential velocity, which is the velocity at B, of this fixed axis rotation around the instantaneous centre is going to equal Vt equals omega times, this time RB, so it's the omega we've worked out is 1.5, well that's just the answer from the last part, 1.55, multiplied by this new length, 0.151, this length. That gives us the magnitude of the velocity of B, which is 0.235 meters per second. Yeah. And now it asks us for the velocity of B relative to A, and as I mentioned, the velocity of B relative to A has got to be perpendicular to this, the link AB. So it's like a fixed axis rotation of B around A. So that's a 90 degrees. So this angle here would be 90 minus 65, whatever that is. And we know from our lecture notes that the magnitude of the velocity of B relative to A is the angular velocity of the link, which we've worked out earlier, multiplied by the length of the link, which is 0.2. So 0.2 multiplied by 1.55, which is the angular velocity we calculated up here, gives us 0.31 meters per second. Right, I'm going to move over here now. So finally, it's asking, in this first part, it's asking for the acceleration of b relative to a in the radial direction. So it's in this direction here. It's the centripetal component. And we know from our lecture notes, again, that the radial component of the acceleration of b relative to a, so here, is equal to the length over which the fixed axis rotation is happening, so 0.2 multiplied by the angular velocity squared. So this is going to be 0.2 times omega squared, which is omega squared is 1.55 squared times 0.2, so that's 0.481 meters per second squared. So that is the those are the answers, the first four parts, and that's I guess the straightforward part. The only complication there was doing this sine rule stuff, but it's just calculating the instantaneous centre. The next parts are more complicated. So we'll take a deep breath. Part 5 says at the instant shown, the link, so I'm going to just draw another, let's move this a bit, and draw another diagram with the same thing. So again, we've got this guide there and a guide there, and the link AB. And it says at the instant shown, the link at point B is moving at a constant velocity. Calculate the total magnitude of acceleration at A and the acceleration of the link. Okay, so if it's a constant velocity, we know that the accelerations at A and B are 0. So let's first of all write out what we know. So the acceleration at A is equal to 0, and we know the acceleration at B is equal to 0. So, oh sorry, no, it only tells us that the point B is at constant velocity, so we only know that the acceleration at B is equal to 0. And we're going to use the result from our lecture. The acceleration of B is equal to the acceleration of A plus the acceleration of B relative to A. And if that's 0, then we know that in this case the acceleration of A is equal to negative the acceleration of B relative to A. Okay, so we know the direction of the acceleration of A. It's going to be along here, and we also know the directions of the two components of the acceleration of B relative to A. So let's expand this out. This is got a tangential component, but you've also got a radial component, and your your tangential component is in this direction, and your radial component is in this direction. So what we're going to do now is create a vector polygon which represents this equation. So we've got the acceleration of A is equal to these two vectors. So let's first of all just draw the direction of the acceleration of A. So this is the direction of the acceleration of A. And then we've got the tangential components. Now, this is again why the question isn't particularly great, because these two components of the acceleration of B relative to A are 45 degrees and 45 degrees from the horizontal, and you can work that out from, if that's 20 and that is 25, then that's going to be 45. So we know these two directions. So something that starts here is going to go along here. Let's say this is the acceleration of A. We don't know the magnitude yet, but there's going to be a direction, of the acceleration of B relative to A tangential component. That's that one. I haven't drawn it quite the same angle. And then that's going to have to add together with a vector that's in this direction, which is in the direction, this is the direction of the acceleration of B relative to A, the radial component of it. So this is the centripetal component, and that's 90 degrees. So that's 45 degrees, that's 45 degrees. So we do know the magnitude of one of these lengths. So this is the acceleration of B relative to A in the tangential direction, but we're not given the angular acceleration of the length, so we don't know that. We do know, though, the angular velocity of the link from the previous part of the question, because we calculated it. What did we calculate it as? Calculated it as 1.55, I think, was it? Yeah. Yeah. So the angular velocity is 1.55 radians per second from the previous part. That means we know what the magnitude of the acceleration of B relative to A is. In fact, I think we might have even calculated it explicitly. That was 0.481 meters per second squared. So that's the length of this vector. So we now know exactly the direction and the magnitude of this vector. Because this is 45, this is 45, this is a right angled triangle, it's symmetrical, this has also got to be equal to 0.481 meters per second squared. So it's asking us what the acceleration of B relative to A in the tangential direction is. Well, that's also equal to 0.481 meters per second squared. So the total acceleration of A, so it's going to be in this direction, because it's there's a negative sign in front of both of these two vectors. So this is the acceleration of A. So it's slowing down. So if that's your link, and it's, sorry, let's do it. Yeah, yeah, that way. So it's going like that. So it's slowing down like that. You see what I mean? We can calculate what that magnitude is by Pythagoras. So that's the square root of these two components, which is 0.481 squared plus 0.481 squared. Okay. Okay, so that's equal to 0.68 meters per second squared. Okay, so it's a bit nasty, but just to recap what we did, we used our expression that we derived in the lecture. Acceleration of b is equal to acceleration of a plus acceleration of b relative to a. We noted that in the question it tells us that's 0, so we now know how the acceleration of a relates to the acceleration of b relative to a. We knew the directions to both of these things and this, and we also knew the magnitude of that because we calculated it in the last part of the question. And from that it was sufficient to construct this vector polygon to give us what the acceleration of a was. Right, let's go on to the final part then. And now it's saying, I have to draw another diagram. Consider now the same position. So, final diagram. Same position, A, B. Now we've got, same again, this is 20 degrees and this is 25 degrees. But this time it says it's momentarily stationary. So that means the velocity at A is equal to 0, the velocity of B is equal to 0, and also the angular velocity of the link is equal to 0. But it tells us that there is an angular acceleration of 4 radians per second squared, clockwise. Now, I think in my solution I draw the vector polygon the wrong way actually, so, but this is the right way. So then, what we're going to be doing is using from the lecture again that we're going to formulate this expression. So the acceleration of b equals the acceleration of a plus the acceleration of b relative to a, and I'll write it in component forms. We've got the tangential component plus the radial component. But the radial component, if you remember, that's equal to omega squared r, in the magnitude of that is. So that's going to be 0 because our angular velocity is 0. We do know what the magnitude of this is. We know what the magnitude of the acceleration of b relative to a in the tangential direction is. So this is going to create an acceleration down here. That's what this component is. And that's generated by this angular acceleration, and the magnitude of it is given down here. It's the length of the link, which is 0.2. So the magnitude is equal to 0.2 multiplied by the angular acceleration, which is 4. So the magnitude of this, so I write it out twice, and is 4 times 0.2, which is 0.8 meters per second squared. So we know the directions of the accelerations of b and a. We know that direction, we know this direction, and now we know the direction and the magnitude of this remaining vector. So that means we've got enough information now to work out what all the magnitudes of each vector are. So we're going to first start by drawing let's do it here, direction, this is the direction of the acceleration of A, and we know that the direction of the acceleration of B relative to A in the tangential direction is down here, and this angle is going to be 45 degrees. This is the direction of the acceleration of B relative to A, tangential component. Then we also have, what am I missing? Acceleration of B, which is in the direction of the guide. So that will be down here somewhere. So I should have had, this is a dashed line because we don't know how long this is. they should all be dashed lines currently. And this is the direction of the acceleration of B. And this angle here, well, if that's 20, then that means that angle is 20. This means that angle is 70 degrees. 70, so 180 minus 70 minus 45 gives you 65 degrees here. So again, a bit of trigonometry just to work out what the internal angles of that triangle are. We know the magnitude of this direction. This is 0.8, so that distance down there is equal to 0.8. So now this is going to be an application of the sine rule. We've got this length of 0.8, we know this angle is 70. If we want to find out what this length is, that's acceleration of B. Then what we're going to do is the sine rule. So this angle, sine 70 over this length, is going to equal this angle over that length. That. So let's do that quickly. So sine 45 times pi over 180 divided by, times by 0.8 divided by sine 70 times pi over 180 should give us our magnitude acceleration of B. So that gives us the acceleration of B is equal to 0.602 meters per second squared, and acceleration of A will be exactly the same, but instead of using 45, we're going to use 65 to calculate this vector here, which is acceleration of A. Okay, so rather than 45, we'll use 65. So that's 0.772 meters per second squared. Right, okay, so that was a bit of a mission, and the question was way too hard, really, but we've done it now, and the questions in your exams won't be quite such a pain.